So let's use this example as an opportunity to think about how you could get areas in between two polar graphs. The logic is pretty straightforward. We're not going to actually solve this one. I think setting it up is enough, since I've already done 2 videos where I've solved. But the circle r equals 6 would look like this. And just to graph this cardioid pretty quickly, when you plug in 0, you get 4 plus 4 times cosine of 0, which is going to reduce to 8. Pi over 2 makes it this to 4. Pi makes it 0. 3 pi over 2 makes it 4. And then when 2 pi brings you back to 8. So it's going to look like this. Probably a little bit better drawn, but maybe I'll just fix it. Alright, so we want I wasn't happy with that, sorry. I couldn't take it. Alright, good enough. We want the area inside the cardioid, but outside the circle. So that's describing this area here. So how are we going to get that area? Well, what you could do is just pretend the circle's not there and get the area inside the entire cardioid from this theta value, we'll just say like theta 1, to this theta value, theta 2. If we can get the area inside the cardioid between those angles, then all we need to do is just subtract the area inside the circle between those 2 angles. So this is the area inside the circle. If we just take the area inside the cardioid and get rid of it, then we'll have what we want. So let's just say that the area of cardioid minus area of circle is what we want. From theta 1, which we'll figure out in a minute, to theta 2. So how do I figure out what theta 1 is? Well, we need to find where the 2 polar graphs intersect. So to do that, just find out where the r values are the same, because at this instant, theta 1, the distance from the pole for both polar graphs is equal. So if we set the r values equal, then that tells us that 4 plus 4 cosine of theta, we want that to be equal to 6. Solving for cosine of theta gives cosine of theta equals 1/2. And so that happens, so cosine of theta equals 1/2 at pi over 3. So that's definitely what we could call the angle 2, pi over 3. Now you got to be careful. You don't want to call, so I'm going to say theta 1 equals, theta 2 rather, equals theta 2 equals pi over 3. You don't want to call theta 1 5 pi over 3, because the limits of integration need to come in order as they would on a number line. So you need to call the other angle, which we know is going to be in quadrant 4, you need to call it negative pi over 3. Right, if you call it 5 pi over 3, you're going to get, you'll be integrating from 5 pi over 3 to pi over 3, which is integrating backwards in some sense, and you're going to get a negative answer, because the angle 5 pi over 3 comes later than pi over 3. But if you write it as negative pi over 3 to pi over 3, then you should get the area we want. So this integral, if we set it up, is just going to be, so again, the area inside the cardioid is going to be from negative pi over 3 to pi over 3, 1/2 r squared So there's our cardioid area, but we're going to minus the area inside the circle. And that expression will do it. Now, if you wanted to do this in one integral rather than two, and then that just sort of leads to the formula I'm going to show you on the next page. But as one integral, you could just write it, because of the properties of integrals, you could just write it as, you could factor out the 1/2 because it's present in both. 4 plus 4 cosine theta squared minus 6 squared d theta. And that would give it. So again, you could do it out by hand. I don't think it's worth it. But the point is that if you want the area inside or in between two polar curves, you got to find where they intersect, the angle values where they intersect, and then it's just a subtraction expression. So we'll formalize this on the next page. So let's formalize what we just did here. Let's call this curve here, R1 of theta. It's just curve 1. And let's call this curve here R2 of theta. So if we wanted, let's say we wanted the area in between, let's say we wanted this area here. So we want that area there, and we'd say we know that this corresponds to an angle alpha, and this corresponds to an angle, theta. Well then, the area between the polar curves is simply going to be the area inside R2 of theta. So that would just be this expression. I guess I'll drop the theta just to, since we don't really need it, minus the area inside of R1 of theta I forgot my differential. But of course that could all be combined into one integral if you're someone who likes formulas. 1/2 R1 minus, or R2 rather, R2 minus R1 squared. Alright, so there's one way to get the area in between two polar curves. Most of your attention will be focused on those limits of integration, because you'll need to find where they intersect, if they do intersect, or you just at least need to know those angle values, and you need to make sure you find theta values that would allow the integral to produce a positive answer. So in other words, the alpha angle needs to be less than the beta angle.